You may have noticed that computations for vectors from abstract vector spaces like Pn are very similar to computations with vectors from Rn. We can use coordinate vectors and then notions of span, independence, basis, etc. And then they become very similar. So in a certain sense, a space like Pn minus 1 is the same as Rn. The mathematical term to describe this is isomorphic, from ancient Greek, iso, the same, and morphe, shape. The idea actually has huge consequences, because you will see this video that in fact all finite dimensional vector spaces are the same as isomorphic to Rn. So, do we exactly mean with that? T from V to W, T linear, is called an isomorphism if this transformation is moreover one-to-one and onto. And then V and W are called isomorphic if such a T exists. And this is denoted by this symbol over here, sort of equality. You can put equality there because they are different vector spaces, but they are the same in a sense. The same in the sense that there is a linear transformation in between them, one-to-one and onto. And then they are called the same, isomorphic. So, for example, Pn minus 1 is isomorphic to Rn. So the polynomials with as highest coefficient t to the power minus 1 is isomorphic to Rn. Well, why is that? We can find this t in between them using the coordinate mapping. The t of this polynomial over here equals the coordinate over here. This mapping is linear, as you know. It's also onto and one-to-one, as we've seen before. So in this case we have a mapping between Pn minus 1 and Rn, which is linear one-to-one and onto, which means that we have an isomorphism between P minus 1 and Rn. So Pn minus 1 and Rn are isomorphic, say the same. Now we have a nice theorem to see whether vector spaces are isomorphic or not. A very strong theorem that says that already the dimension is enough, well, as long as they are finite dimensional. So if we have two finite dimensional vector spaces with the same dimension, then they are automatically isomorphic. Extremely strong property, of course, because the dimension of a vector space is just a number, and this number already tells you whether it's isomorphic to another vector space or not. So you immediately see that Pn is not isomorphic to Rn, because the dimension of Pn is n plus 1, and the dimension of Rn equals n. And this has a big consequence, of course, because it means in particular, if you have an n-dimensional vector space, then its dimension is n, the dimension of Rn is also n. So you know that if you have any n-dimensional vector space, it is immediately isomorphic to Rn. That's the third example. So sketch of the proof of this strong theorem. Well, first, if they are isomorphic, then you have this mapping which is linear onto and one-to-one. So in particular, because this mapping is one-to-one, nullity dimension of null space is 0. So the rank of T equals the dimension of V minus the nullity, so the dimension of V. And this has to be able to the rank of T has to be able is the same as the dimension of W, because you are onto. So those are the same. Rank of T equals the dimension of W equals the dimension of V. So if they are isomorphic, then the dimensions are the same. Other way around, if the dimensions are the same, you have to find this mapping that is linear and one-to-one and onto. You use the following trick. They have the same dimension. They are finite dimensional, so they have both a basis. So basis B for V and a basis C for W. And how do you find this mapping? Now, you can express any V in terms of its basis, C1, V1 plus Cn, Vn. And how do you find this mapping? Well, you find the corresponding W, define the T of V with this same coefficients. And then in that way, you find W into your vector space W. This mapping, well, this is just a sketch. You still have to prove that this mapping is linear one-to-one and onto, but it is. And with this mapping, you show that if the dimensions of vector spaces are the same, then they are isomorphic.